Exercise 1018 is meant to help you practice with the acid-catalyzed hydration of an alkyne. This is really similar to a reaction that we learned for alkenes. You add water and an acid. In this case, it's going to be sulfuric acid because of the catalyst that we have to use with alkynes. But you might remember this from alkenes just as being H3O+. I mean, that's technically what you get when you mix this together, because the sulfuric acid is a really strong acid. It gives all of its H's away, and so water just accepts those H pluses and turns into H3O+. So they have been relatively synonymous up to this point, but you really should use specifically this recipe rather than H3O+ when you're talking about alkynes, because the acid should match the catalyst. This is a catalyst that was developed historically. People saw that it improved yields for the reaction. And so that's mercury 2 sulfate, or you could call it mercuric sulfate. That's the one new addition here that's used to increase the efficiency of this reaction, this acid-catalyzed hydration, when you're doing it to alkynes. So you don't have to add this when you're doing this reaction to alkenes. Now, if you remember from the alkenes, what this does is it adds an H and an OH in a Markov-Nikov way, and you take away one pi bond. You use the electrons in one pi bond to do that. Now, I won't draw the mechanism. If you're curious for the mechanism for this, I encourage you to go back and watch the video. There are a couple of them on drawing the mechanism for acid-catalyzed hydration of alkenes from the previous chapter. But what you get after the first reaction, what you would predict from the previous chapter, is you'd add H on the less substituted carbon, OH on the more substituted carbon. So if you were doing this exact reaction with this molecule, at first you would expect to get this. And notice that what we have here is an enol. You have an alkene and an alcohol. And so it tautomerizes using that mechanism that we drew in a previous video in this chapter. And after it tautomerizes, the hydrogen changes place, right? You have the 2 proton transfers, and you end up with this ketone, which you can see is what the product you're getting. So the mechanisms we've seen for these things in other places, so I don't want to stress them here. This video is to practice predicting the final product that you get. But it's important, it makes it much easier to remember that if you do know what's happening in terms of the mechanisms. So I encourage you, if these don't look familiar, to go back to the previous chapter and see the mechanism for acid-catalyzed hydration. And then, in this chapter, go back and see the mechanism for keto-enol tautomerism. In general, though, if you are just trying to predict the product, in this case, you're going to put a double bond to an oxygen on the more substituted carbon in the alkyne. Everything else turns into single bonds. So let's try that with some larger molecules, different molecules. So let's start with this one here. And you can see that's what the instructions are telling you. They say, draw the major product or products expected when each of the following alkynes is treated with aqueous acid in the presence of mercuric sulfate. That's the HgSO4. Okay. So what you can do is redraw the exact molecule just with all single bonds. And I encourage you to number these. So let's say 1, 2, 3, 4, 5, and then we have that 5-membered ring. So I'm going to redraw a 5-carbon chain. So 1, 2, 3, 4, 5. And then attached to this, I'll have that 5-membered ring, so like that. Okay, well, carbons number 1 and 2 were where the triple bond was. That's where the reaction is going to happen. And if we're just trying to predict the products for acid-catalyzed hydration, you want to see which is the more substituted carbon in the triple bond. Notice this one here is only bonded to one other carbon, so it is primary. And this one is bonded to 2 other carbons, so it is secondary. Notice this one is the more substituted one. On that more substituted one, put a double bond to an oxygen. And that's your product. When you treat this alkyne with water, sulfuric acid and mercuric sulfate, you end up getting that ketone. And a ketone is a molecule that has a carbon double bonded to oxygen, single bonded to carbon on each side. So that's a ketone. And that's spelled like that. The ending ONE in names represents a ketone. So for example, testosterone is a molecule that has a ketone in it. Okay, let's try the same procedure with another alkyne. Now again, the mechanism is there for you to explore in other videos. Here we're just trying to predict the products. So, redraw the molecule just with all single bonds, and it's very easy to get the wrong number of carbons, so make sure if you're practicing and you're finding that you get the wrong number of carbons, to number them. I think it helps a little bit. So we have 4 carbons here in a sort of straight chain. So I'm going to draw 1, 2, 3, 4. I'll number those again. On carbon number 3, I have 2 methyl groups. So 1, 2. Okay. So now all I have to do is put the ketone on the molecule. I have to put the double bond to an oxygen on the more substituted carbon in the triple bond. The triple bond is between carbons number 1 and 2. So I know that the double bond to the oxygen is going to be on one of those carbons. It's going to be, because this is Markov-Nikov addition, the hydrogens go on the less substituted carbon, and the oxygen will go on the more substituted carbon. Notice that this carbon on the end is only bonded to one other carbon. It is primary. The carbon in the middle is bonded to 2 carbons. It is secondary. And so the double bond to the oxygen is going to go on the more substituted secondary carbon. And so that is the ketone that you would get if you treated, well, here, this is the ketone you'd get if you treated this alkyne, that alkyne with water, sulfuric acid, and mercuric sulfate. Notice that these are all just in one step. They're all mixed together in the same beaker or flask. Okay, let's try another one, C. So here, count the carbons and redraw the molecule with all single bonds between the carbons. So here we have 1, 2, 3, 4, 5, 6, 7, 8. And be careful, remember there's a carbon at each end of the triple bond, so don't skip over those just because they're linear. So you have 8 carbons. Well, here we have 1, 2, 3, 4, 5, 6, 7, 8. And I'll number those to make sure I'm putting everything in its right place. Okay, the triple bond is between carbons 3 and 4, so I know that's where I'm going to have my double bond to the oxygen. Now in this case, this is Markov-Nikov addition, but in this case, both of the carbons are secondary. If you see, this one here is bonded to 1, 2 carbons. This one here is also bonded to 1, 2 carbons. So both of those are secondary, and so there is no preference for where the oxygen should go. And what that means is that you're going to get 2 products here. Because the oxygen would normally go to the carbon that's more substituted, but since they are equally substituted, you will get an equal amount of the oxygen on each carbon. So on 1, the double bond to the oxygen will be on carbon number 4. But in another molecule in the mixture, the double bond to the oxygen will be on carbon number 3. And so, if you did acid-catalyzed hydration with this, you would get a mixture of 2 products. These 2 ketones here. Okay. So now in D. So in this one, yet again, number the carbons. I would recommend you to number the carbons and then just draw a straight chain of carbons with all single bonds. Be careful, make sure you number the carbons in the triple bond, even though it's linear. You have a carbon at each end of that. So 7, 8. I like to circle this just so that the branches really stand out away from this. So we have 8 carbons. And so we'll have 1, 2, 3, 4, 5, 6, 7, 8. And I'll number those just so I can keep track of where I'm putting everything. So 4, 5, 6, 7, and 8. Okay. In the original molecule, we had a branch on this carbon number 2, a methyl branch. And we also have a methyl branch coming off of carbon number 7, so I'll put that in there too. The triple bond was between carbons 4 and 5, and you'll notice that just like last time, those are equally substituted. Both of these carbons are bonded to 2 other carbons. So they're both secondary. And so there's no preference for the double bond to the oxygen to go on one over the other. You would get a mixture of it going on both. So in some of the molecules, it would go on carbon number 4, and in some, it would go on carbon number 5. Now notice these are actually, because this molecule is symmetrical, these are actually the same molecule. I don't think I would take points off necessarily if you listed it twice, but it's good to be able to see. If you take this molecule and you flip it over, notice it's the exact same thing as the one on the left. So because the molecule is symmetrical, you don't have to draw it twice, but I guess you could. It's not the biggest deal. So if you treated this with this alkyne at the top with water, sulfuric acid, and mercuric sulfate, HgSO4, you would end up getting this ketone down here. Ketone, carbon, double bonded to oxygen, with a carbon on both sides. All right, E. So with E, we have a ring, and so we're going to be keeping the ring. This reaction doesn't break any sigma bonds, so we should number this. I'm going to number the alkyne as carbon number 1, and then I'll just go around. So 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to have an 11 carbon ring. Now, really, you might just copy the structure from the top, except for where the alkyne is. So this should be, this is like carbon 3, 4, 5, 6, 7, 8, 9, 10, 11. So we just need carbons number 1 and 2. And we could have that mimic the top. So if we had carbon 1, 2, there we go. It looks a little strange, but it's an 11-membered ring. So good enough. Now, if your ring looks really weird like this, the one thing I would really encourage you to do is number it for me, so that if I grade it, I can tell how many carbons you meant to have in your ring, because this these larger rings are sometimes really cumbersome to draw. Okay. Well, the important thing is to know how the functional group changes. And the functional group here is between carbons number 1 and 2. And you'll notice that those are equally substituted. Both of those are secondary. Both of these carbons are bonded to 2 other carbons. 1, 2 other carbons. So they're both secondary, which means that you would get a mixture of the triple bond, or I'm sorry, the double bond to the oxygen, going on both of them. So you could have it going here, or you could have it going on the other carbon in the triple bond, carbon number 1. And truly, this, either way, I know it kind of doesn't look like it with this weird looking ring that I've drawn, But either way, the molecule will be symmetrical, and so it's the same thing. But if you just want to cover your bases, you could put the double bond to the oxygen on either one. So you would get a mixture of those two of those two ketones. If you treated this alkyne with water, sulfuric acid, and mercuric sulfate, all in one cauldron. And that is hopefully gives you some practice in the sense of just a sort of foundation for what it looks like when you treat alkynes, when you do acid-catalyzed hydration to alkynes, when you treat alkynes with water, sulfuric acid, and mercury 2 sulfate or mercuric sulfate.